Hello, so far in this module, we learned how to put together a multiple linear regression model and what should be the rules or guidelines to follow and how to check Vif values for multiple linearity. In this video, hopefully this will be concluding multiple linear regression. We are going to understand how we can actually split a given data set into train and validation set so that we can form our multiple linear regression model with the training set and we can validate it on an unseen data on the test set, okay? So we're going to be working on this specific data file called Hightex, and this is a company. They do keep records of their customer spendings, and what they have here is the following. They do have customer IDs, and then they do keep their age, their gender, on whether the customer owns a home or not, married or not, and then the close column represents if close to stores with similar. Okay, so if close column has 1, it means that so I think the store is close to the merchant size. The customer store is close to merchant size. If not, it is taking a 0 value. Well, obviously you realize that these are all owning a home, married, and close columns are categorical independent variables. And age is numeric. Salary information, we do have that as well. And the number of children is numeric as well. And we do also have previous customer. If it is 1, it means that it's a previous customer. If it is no, it is not a previous customer, and therefore this is also a categorical decision variable. And then we do also see the previous spent dollar amounts here. And we do have the number of catalogs sent to these individual customers. Eventually, our job is to try to explain the total amount spent by these customers giving these information, right? How do we do that? Well, the question adds extra layer of complexity to it. Well, not the complexity, but direction to it. It says that you have to base the regression on the first 750 observations and use the other 250, last 250 for validation purposes. So let's see one more time what the data look like. So the data has 1,000 customer information, okay? And then in this 1,000 customer information, we are going to be using the first 750 of them for forming our multiple linear regression model. And the last 250 records are going to be using for validation purposes. Why is this important? Because once we use the entire data for forming a multiple linear regression, actually we are cheating because model already saw those data sets, right? Therefore, it is wise to split your data set into 2, either like 70% versus 30% or 80% versus 30%. Some people use 75% versus 25%, which is fine. To split the data into 2, the larger amount of data set are going to be mostly used for training the model. In this case, it's going to be multiple linear regression model. And the other remaining portion is going to be using to see whether the trained model is performing nicely on a data set that's not seen by the model. Because when we go ahead and implement this model in the future, well, guess what? We will be making predictions for the future unknown data sets. And we want to make sure that that works out just fine for us. Okay, let me close this and then let's go to R and import our Hightex data. So I already posted this on Canvas, so you should have no problem reaching it. And it is module 3, chapter 11, Hightex data. Make sure that it comes up, the name comes up as Hightex, and it looks good. I imported it. And I click on this data frame and I see that those are all numeric. Well, R does not understand automatically that gender, home, owning a home, married, close, and I think there was one more. Previous customer columns are categorical. So that's our first job to tell R that these columns are categorical. How do we do it in R? We use as factor function, right? We literally will call individual categorical columns, and we say that go ahead and implement as factor, make them categorical by using this function. And again, save them in the same column, right? This is what's going to happen with the iText categorical column. So let's first try to see the structure of this. And you also see similar information with the structure function. Right, so those are indicated as numeric, not categorical. I think I've missed out one more categorical column, and which was here, I think previous customer or not. So we also have to convert this numerical column into categorical column. So I'm going to highlight all these 5 rows, and I am going to execute this. Okay, so what it did is, let's call one more time the structure of the iText. Let's copy and paste it here, and then this will show you the changes. So it already made the previous customers a factor or categorical variable with 2 levels, right? It also tells which is 0, which is 1. Owning a home, married, close, and gender, those are all categorical now. So it worked, okay? So if you have categorical information in your data set and you're trying to transfer them into R and try to build any multiple linear regression model, so you can do it like this. So now our job is to actually get the first 750 of these rows, right? And then store them in train data. And how do we do it? Well, in data frames. So these are all data frames. And what happens in data frames, we can reach out to records in square brackets. So we do have iText data frame. We already imported it. And what the left side of this comma does is it actually tells R to grab the rows from 1 to 750th row, including 750th, and all the columns, right? We leave this right side of the comma empty, but it understands that you are actually looking for all the columns in this data set, but only the first 750 rows, okay? So let's execute it. And then we would like to keep this in a different data frame. We are going to create a different data frame called train data. Minimize it so that it will appear here. Let's execute this. And then as you can see, this train data has 750 observations of 12 variables. Then can actually call the structure of it. You see that similar structures for each column, but only the first 750. Well, how about the last 250 rows? Well, we can actually utilize the same structure, but this time we are going to keep it under test data, and then we will be looking for the last 250 rows and all columns, okay? And this is how we can retrieve your test and train data. Some people call it test, some people call it validation, but they are both actually referring to the same thing, okay? What we are going to do, actually, we are going to start with our entire set of independent variables here. So what do we have? We are not going to include customer here because those are basically IDs, but we're going to include age, gender, owning a home, married, close, salary, children, previous customer, previous spend, catalogs as independent variables on predicting amount spent, okay? This is what this LM function does, and I'm going to keep this under this name. Again, names are not really important. You can give it to any name as long as you use the name consistently. So let's execute this line. It ran the regression. Let's see what the results say. Again, this is just the first regression that I'm putting together, but I'm not going to deal with dropping these independent variables one at a time based on their p-values. You could do it, but I'm going to use a semi-automized way of doing that, in which is step AIC function we just saw. Okay, so remember, for step AIC function, you have to have a linear regression model, and then we do already have one, right? So I am going to keep this step AIC model, the ultimate step AIC, the ultimate regression model found by step AIC under this name. And on the first spot in the step AIC function, you put the regression name of the regression model. And then we specify the direction. We just ask it to go ahead and do backward and forward selection to get us the best regression model. Okay, I execute this line. You could actually, before you hit summary step high text, you could actually come over here to see in each iteration what it did. Well, it started with the whole model and it tried all these iterations. So it basically tried to remove married, age, owning, home, all the way down to salary. And it looks into the AIC value. So this is the error values. As long as it is shrinking, it is good sign. And then in the second model, I think it removed one of them, but I don't know which one it removed. I think in the married column, yeah, married column went away. And then it tried all these all these operations. It tried adding back married into it, and then it sees that actually removing age is also a wise thing, right? Age is no longer here, married is no longer here. And then it tried all these bunch of other stuff. And I think owning a home went away as well on the last one. I tried all other information, all other iterations. So let's see what the end result was. The good thing is I didn't have to do this by myself, right? So it was automized. So let's call summary step high text to see the end result, okay? So it basically gives me this. So it tells me that I do have gender, clothes, those are categorical information, right? Those are the reference columns. And then those are kept here. Salary, children, previous customer, one. And this is again categorical. I keep that. Do you spend and catalogs? Let's check out the multiple square value is not bad. I could explain 75% of the variation in the amounts spent by the data that I have with these independent variables. Significance of regression looks good. There's one thing that you can do here. As you can see, the p-value of gender column is actually greater than the level of significance 0.05. You have to make an executive decision here. It is not really that high. And if you like to get rid of this, I think you're going to lose R square, right? So, and the model wanted to keep it that way, and I'm going to hold on to it. Although it is violating a little bit, but I'm going to keep it for the sake of learning more about my model, okay? You can make these great decisions by yourself. And then last step is to check the VIF values. So I check the VIF values. Remember, the key is the VIF values, if they are less than 5, we are good. Sometimes, most of the time we check it against 10, but if they are less than 5, we are safe to say that there is not really a multicollinearity issue here. In this case, we don't, so we stop here. Okay, so we just fit a multiple linear regression model on a trained data on the first 750 rows, right? The model hasn't seen the last 250 customer information. Let's see how it is going to behave. I'm going to take this model and I'm going to try to predict the amount spent on the customers that the model has never seen before. This is cool. I mean, this is really cool because we are going to get to do our first validation. And how do we do it? We actually come over here. We are going to use the predict function. By doing what? By using step high text, the step AIC model that I just created here. This is going to be indicating the last model that this step AIC concluded, right? I'm going to use this model on the test data, okay? Remember, in this LM function, I use the train data, but here on the product function, I'm going to be asking this step high text, the last model that I concluded with, to be run on the test data set the model has not seen before. And I'm going to be keeping them in predicted amount spent in a different data frame. All right, let's run this. Let's execute this line. You see that it actually added our values into it. It's not a data frame, I think it's a data series. And then let's display them. looks like this. Like this is the prediction that our model made for the last 250 observations. Well, the first observation, the predicted value was 2084.6. So if you go to the test data and look for the amounts spent, the first value was 2,183. Well, it is close, right? The second observation, actually, it was 2551, 2975. It's a little bit far off. Well, is there a better way to check them? Yes, there is. What we can do here is we can take this predicted amount spent and use it as a column in the test data, right? We can surely do that. And how do we do it? Well, we go to test data, open the square brackets, and in square brackets, we can type the name of this column that's going to appear at the end of the test data frame. And then we can literally just say, go ahead and in that new column that you created under this name, use this information. It's going to be lining up very nicely. Let's execute this. And let's call view test data line. It's going to open up the test data in a different window so that we can take a look. If you scroll to the right, what you see here, it just added this predicted column, right? We changed the name to predicted, right? And then we used actually the predicted values here, right? And then we can actually take a good look at what's going on. So yeah, the first amount spent actual value was this, and then the predicted value was that. And then if you just scroll down, you see the predicted versus actual values. Well, can we see this in a visual representation? That's something that I would like to do. Yes, we can simply by using the plot function. What I can do is I can actually put the predicted value on the y-axis and the amount spent on the x-axis. I can change the axis labels like this. If I just run this plot, I do see that this is actual spend versus predicted spend. If I had a perfect linear match or perfect match between my predictions and actual spends, I would have seen all these circles on a constant line, right? 45% angle. Let's add a trend line to see how well this is a fit. Well, it's not really a bad fit, right? It is not really a bad fit. I could see that my regression line is just making a good representation of the actual spend versus the predicted spend. Well, guess what? My R-square value was 75%. It means that actually by using this data set, I could explain 75% of the change in the amount spent, okay? Well, in a nutshell, this video shows you how you could split your data set into training data and validation data, and how you could fit a linear regression model by using the training data. And later on, how you can actually implement that model on an unseen data like this, right? Thank you so much for your attention. I will see you on the next video.